don't know about you guys, but I'm already over today.
Oh, yeah.
Oh, yeah? So my alarm didn't go off this morning because on my phone I shut it off last Monday because we had Labor Day. So woke up late, which meant I left home late, and I have a 50-minute drive to get here, full of down debris, cars driving slow, which is a good thing, okay, but slower than I was thinking. And I walked in like 5 minutes probably before I had to be here, so I'm already done. Yeah, checked out. All right, did we try any of the graphs over the weekend for the homework assignment? Do we want to check any of them? Go over any questions you may have had? Speak now, forever hold your peace. Yeah. Number one? Sure. All right, take a look at number one. What type of parent function should we be starting with? What should it look like? What's the name? Go, Rebecca.
Quadratic, so it should be like
How'd you know it was quadratic? That's good. It's squared. Okay, so that power of 2 is telling you a quadratic. So we're going to start with that parabola type shape. That U. Okay, so the power of 2 is telling you the type of original parent graph. All the other numbers or symbols are telling you how you're changing that graph. Can we identify some transformations? Left, right, up, down, flip, stretch. Any of the above? Yeah.
You're going to go, it appears that's minus, it's minus, you're going to go right 3 and then up 5.
Okay.
And then you're also going to have an x-axis.
And x-axis flip. Okay. So the negative out front is x-axis reflection. And then the inside does the opposite of what you'd think. I know we're subtracting 3, but it's actually going to make it go right. And then plus 5 on the outside goes up. Okay, so our order, RST, we labeled a reflection. That's the x-axis. So all of these points on the parent we're going to flip over. Right, so there's your R graph. We did not label any stretches, so it's one less thing we have to do. And then the translations, the up, down, left, or right motions, we have to move all of these red points right 3 and then up 5. It looks like on your graph, maybe it didn't print correctly, but there should be kind of a line going through right there. So you can label that one as your final. Is that okay? Yeah. Okay. Any other ones? Yeah. 2. Okay. What should our parent function look like? Our starting graph. I think we have 5 that we've talked about so far. Yeah?
It should have a segment on the one end, and it should kind of have like a curved arrow in the middle.
Okay, so it's kind of like half of a parabola on its side. Okay, we have that square root function, because we have a square root in our equation. So let's go ahead and label what all of the other symbols or numbers are telling us to do. Any transformations? Yeah.
Reflection of the y-axis.
Y-axis, okay. I'm just going to label it Y there. So that's a y-axis reflection. We're folding it from right to left instead of up to down. What about any other ones? Yeah, keep going.
Right 2 and up 3.
All right, so typically the +2 on the inside would make it go left, but we gotta be a little careful because of that negative on the inside. It actually switches the direction. So this one would go right 2 and then up 3. All right, so same order, RST, we labeled a reflection. So all of these points on the right-hand side have to be folded over the Y and now go into the left. So there's the reflection. And then all of those points, we did not label any stretches, again, which is good. But then we have to move them right 2 and up 3. So you can label that one as your final. Dylan, did you have one you wanted to go over?
That was the one.
That was one? Okay. Yeah.
This isn't going over one, but in theory, if you have one like number 1 where there was like a -4 on the outside, so would you like flip it over the x-axis and then like change the stretch forward?
Like if right here was -4.
Yeah.
Okay, so the negative is telling you x-axis flip, and then the 4 is that vertical stretch.
Okay. So
Each little thing does something.
Okay.
Yeah.
They'll never be like, you'll never scrunch something down because of a negative.
No, no. I mean, if it was -1/2, maybe we would make it smaller. Okay, but the negative are only flips. Okay, good question. Any other ones? All right, let's look a little bit more into transformations today. We're going to focus on the ordered pairs. Remember on Friday we filled out that very nice organized chart with all the different ordered pair relationships, like which value did we affect, either the x or the y coordinate. We're going to go over that again today and take a look at some examples of just coordinates, not necessarily graphing a picture. We're just going to take a look at the coordinates from the points on the graph. So we've talked about, I think there's about 7 different transformations that we can apply to a graph. Let's go ahead and refresh our memory of those 7 transformations and how they affect the coordinate, either the x coordinate or the y coordinate. So out of all the transformations we've been discussing, can we rattle off some of the different ways we can move or change a graph? Yeah.
Reflect over y or x-axis.
Okay, so we're going to say reflect x-axis. That's one type of change we could do. And while we're at it, maybe we'll discuss the y-axis as well. Okay, so if we were to reflect it across the x-axis, maybe you have to reference your chart from Friday to help you out. Which coordinate do we affect and how so? If we flip a point from above the x-axis to below the x-axis, are we changing the x or y, and how are we changing it? Yeah.
How are we changing the y being negative or opposite?
Okay, so y changes sign. It becomes the opposite value. What about an x-axis if we want to fold it right to left? Which coordinate are we affecting and what are we doing to it? Maybe you can make a connection. If we reflect it across the x-axis, the y changes sign. So therefore, go Dylan.
The x changes sign.
The x changes sign. Okay. Looks good so far. Evan gave us 2 of them. What are some other things we can do to a graph? How can we change it? Good, Hannah?
Vertical stretch?
A vertical stretch. You guys are doing all the difficult ones first. Okay. In my opinion, these are the difficult ones. Okay. Maybe we have a vertical stretch or shrink. Okay, we haven't really seen one of those yet, but we can make a graph smaller. Okay, we can shrink it down. So if we're going to vertically stretch our graph, which coordinate do we change and how do we change it? Go, Rebecca.
You change the y and you have to multiply it by the number
Mm-hmm.
that is being stretched.
There we go. So if we had a vertical stretch of 4, we would multiply all the y's, aka the heights, by 4. Maybe we had a vertical shrink of a half, we would just multiply everything by half. Okay, bring those points down, or bring the heights down. Looks good so far. What about some other ones? How else can we move or change a graph? Can we go up? Yeah. Can we go down? How about we throw in some left and right as well? All right, if we shift a graph up, which coordinate do we affect and how do we affect it? Yeah.
You affect y because you add a number to it.
Okay, so we're going to add to y. Well, maybe we'll say add to y. I don't want to write add y because y isn't the number we're essentially adding. Okay, what about down? Which coordinate? Yeah. Subtract from y. And very similarly, if we're moving left and right, if we're moving left, we can subtract from x, and then right, we would add to x. Is that coming back to us from Friday? We filled out that chart? Okay, we're going to use this summary, I guess, to help us with the table down below. So you might not see it on the board, but you have it in front of you. Okay, I'm going to shift this up a little bit. So the table below shows some ordered pairs of a function. And it says that they consist of line segments connecting the points, so your graph might look very jagged if we were to actually graph these on a grid, but we're not going to do that. We're going to use the table of values below to identify what transformations are happening and how those transformations affect the coordinates, aka the table itself. So what we're doing here, take a look at how number 1 is written here. The new function g of x is said to be the transformation of the f of x table. So we're going to take the f of x table and somehow change the values, and that's going to give us this new graph or new function that we name g of x. So can we identify some transformations that are being done on the right hand side of this equation? Are we adding anything, subtracting anything? Are we flipping anything? Can you tell based off the way it looks? For instance, we're adding 2 on the outside of the function. We have a negative on the outside of the function. What are we doing to this table or this graph? Those values. Can we label them? Go, Tori.
Changing the value of all the y's.
How?
Like switching your signs.
Okay, so we're switching the signs. This is a reflection over the x-axis. Okay, and if we're adding 2 on the outside, we're going to go up 2. So what I want to do is somehow relate what these transformations are doing to the ordered pairs. For instance, on the original table, we have an x-coordinate and a y-coordinate. Those are the starting points that we have. But on this new function, g of x, what might the coordinate look like if we are applying an x-axis reflection and we're going up 2? Take a look at our summary at the top. What do we have to do to these original x's and y's to get our new coordinate? What do you think, Hannah? Change the y somehow. Okay, so if we take a look at the x-axis reflection, we said that the y variable changes sign, right? So instead of being a normal y, it would have to be a negative y, right? Changes sign. Okay. We also said that we are shifting every point up 2 units. And if you take a look at your summary, if you move up 2 units, you have to add to the y variable. So we're going to go ahead and add 2 to the y variable. Does that make sense? Okay, we're not affecting the x in any way, so notice how the x is just staying in x. Both of those transformations, though, are affecting the y coordinate. So f of x is the original point based off the table, but now we have some type of formula to help us figure out what the g of x points or table might look like. So let's go ahead and try to fill out this chart on the right. So on the original f of x grid or table, we have -3, 5. You can see that's your first kind of ordered pair. We're going to try to figure out what's the new g of x coordinate, what's the new x coordinate for g, what's the new y coordinate for g, and therefore what's the ordered pair, like the actual point. So if you take a look at what we have here for g of x, we said the x coordinate will never change. So if it starts as a -3, it's going to stay a -3. But the y value on the hand, we have to make it the opposite and then add 2. So notice how the original y value is 5. If we make 5 the opposite and then add 2, notice how we'll get -3. Right? So the new point on this g of x equation, we'd have -3, -3, based off the transformations that they gave us. Do you guys think you can fill out the rest of the table? All right, go ahead and give it a shot. Can we rattle them off? I think the x's are easy, right? They're all just going to stay the same. What about the y coordinates? Can we just go ahead and shout it out? Yeah. 1. Okay. 6. So far, so good. 1. 0. 4 for 4. Okay. So there are the new coordinates of the g of x function with the transformations being applied. If you wanted to graph it, you could, okay, just to get a visual, but we don't really have the graph to actually do that. Okay, let's go ahead and try another one. I think you guys are getting the hang of it already. All right, so very similar. We have a beginning table. Okay, this is the original. You can think about this as the parent one, the one that you start with, and then we're going to transform it somehow.
Please excuse interruption. Bus 11 is just now arriving. Please admit them into your classroom. Thank you.
All right. Can we identify some transformations in number 2? Based off the way the equation looks? Notice how we're multiplying by 3 on the outside, adding 2 on the inside, and then subtracting 3 on the outside. Good, Marie? All right, vertical stretch. What about those other ones? Good, Marie? This one is moving down. This one actually moves left. Does the opposite of what you think. Inside's always tricky. Okay, so we are starting with these original points like x, comma, y. What are the transformations going to do to those coordinates? Okay, this graph or function is now called h of x. So can we write the little formula for the new ordered pair based off those transformations? You want to give it a shot, Tori?
-2, -3, or -3.
There we go, 3y minus 3. All right, so vertical stretch, we multiply the y by whatever number that is. So notice how we have a 3 times y. Left, we have to subtract from the x. So we're subtracting 2 from the x. And then down, we got to subtract from the y. So also with the y, we have that minus 3 based off those transformations. We doing okay? All right, so let's go ahead and fill out the table. We have the original coordinates on the left. We're going to fill out the new x coordinate for h, the new y coordinate for h, and then put them together to write the ordered pair. So for the x coordinate, all we really have to do is subtract 2 from all the terms. Did I miss something?
No, this is off topic.
Yeah.
Can I close the door?
Oh, yeah, sorry, go ahead.
No, I can't hear
You can hear? Sure. I got some loud colleagues. Okay, so for all your x's, we just need to subtract 2. Y's, though, are a little bit more involved. You got to multiply 3 and then subtract 3. How did we do? Pretty good? All right, I want you guys to try number 3. Give it a shot. We'll do number 4 together, but go ahead and try 3. We're still using the same table from the top. Yes.
Can you take the negative outside the parentheses into consideration for this one because for this one?
For number 4?
For number
3? You mean this guy right here?
Yeah.
That one is telling you just an x-axis.
Okay, so it doesn't affect it like the
No.
other
No. If it's on the outside, doesn't affect it. Inside, though, yeah.
one.
Okay? The inside, again, is always the trickiest part. Okay? And we're going to see that in number 4. How do we do on 3? Can we get those numbers? You tell me if you weren't, right? Okay. Let's go ahead and take a look at 4. I want to try this one together just because it can be tricky with this whole inside stuff. Can we identify any transformations? Go, Tori. Y-axis. Anybody inside? Keep going, yeah? Right 3, good. Typically it would go left, but we have that negative on the inside, which changes it. Okay, and then last one? Yeah. Down 2. Okay, so if the original parent points are x and y from the table, let's write what the new points would be for this q function. So y-axis reflection, go ahead, Tori. Negative x plus 3. Y minus 2. Okay. Y-axis reflection switches the x value. Right 3, we got to add to the x coordinate. Down 2, we're changing the y's, so we have to subtract. Alright, so let's check out what our new coordinates are. The x coordinate, we have to switch the sign and then add 3. So if we switch negative 3, it'd become positive 3, and then add 3, we'd get 6. Switch the sign on negative 1, add 3 would become 4. Switch the sign on positive 1, add 3, become 2. Switch the sign on positive 3, but add 3 would become 0. Switch the sign on positive 5, and then add 3, we'd get negative 2. The y's are a little simpler. We're just going to subtract 2 from all the y coordinates. And based off those, we can write our new ordered pairs. Get the hang of them? Perfect. All right. So those are ordered pairs based off of transformations. No graphical pictures, okay, but at least we can figure out some ordered points. And if we had to graph them, we could just simply graph those ordered pairs. All right. Let's go ahead and transition to graphs, okay, because we've been doing those last week. But this time, we're going to take a look at piecewise functions. We've seen these before, okay, where you have multiple graphs, multiple pictures on just one coordinate, okay. I know every teacher goes over these in a different way, and I'm not sure what you guys are familiar with in terms of graphing piecewise functions. I'll show you how I tackle them, okay, just because that's what I'm used to. But in my mind, I'm not concerned how you do it, as long as we can get the correct picture. Okay, so whatever works for you, you do you. All right, so when we take a look at number 1, the first thing that I normally look at are these domain pieces. I think we talked about that last week, right? Domain and range, very briefly. Remember, domains are the x values that work. So they're telling you up here that numbers between -1 and 4, okay, including 4, because we have that bar, are the only x values that work for this first equation. But you can pick any number greater than 4 that you want, and you would be able to plug it in to this equation. So we only have certain x values that work for these different pieces. So what I do is I kind of section off my graph. For instance, this -1 is the lowest x value for the first piece, and then +4 is the highest x value for the first piece. But notice how +4 is the kind of the beginning value for the second piece, right? So I immediately section off my graph and I label which equation goes in which section. For instance, the first equation is only going to show up between these two little barriers that I drew. The second equation is only going to show up on this right side. Does that make sense? So if I'm plotting points for this second equation and they're being plotted over here, I don't have to plot them because they're not even supposed to show up in that spot. Okay? Sometimes I'll write none over there because according to the domain pieces, we should have nothing in that section. I'm not saying you have to do that. I'm just saying that helps me remember when I actually go through and graph. Okay? So the next thing that I do is I start with these easy numbers that they give us, okay? Because we know if we plug in -1, we should be able to get some type of location, and if we plug in 4, we should be able to get another location. Excuse me. So let's go ahead and plug in -1 into this first equation for the x. We'd have -1 minus 2, which is -3. If we square that, though, -3 squared would be +9, and then if we subtract 3 we would get 6, right? So if we plug in -1 we get out 6. Let's go ahead and plot that point. -1, 6. Now, so we're somewhere right here. Can you determine based off of that domain whether we should have an open or a closed circle? How can you tell? Should I put a dot there or should I put a little open circle there? What do you think, Rebecca?
The circle should be open because it is, according to the sign, it does not include -1.
Right, okay, so you're technically figuring out here if you could plug in -1, where would your graph be? But notice how we cannot equal that -1 point because there's no bar, so we should put an open circle there. The open circle is just telling you that's where you would be if you could, but you can't, so it's open. Let's do the same thing for 4. Okay, if we plug in 4, 4 minus 2 is 2. 2 squared, we got 4. 4 minus 3, we got 1. So if we plug in 4, we get out 1. Notice how there is a bar, so we can be that point. We'll make it a closed circle. So somehow I need to connect this open circle to this closed circle. How am I going to connect them? Am I going to draw a straight line? Am I going to draw some type of curve? Is it going to look like a thunderbolt? Like, how do I know to connect those 2 points? How can you tell? Any idea? Can you tell based off of how this equation looks, what type it is, what parent function we had? Go ahead, Tori. It's a quadratic. Okay, so we should have a parabola, some type of U shape. Now the question is, I don't know if the U goes up or down. I don't know if it looks like this. I don't know how low it goes or how high it goes. Okay, so we need to figure out some other point in the middle as like a guiding point in terms of this U. Okay, so that's where we're going to take a look at the transformations. If you think about a typical quadratic, it starts at the origin and kind of goes up from there, right? So let's maybe see if we can figure out what that vertex point is or where it's located. So if it normally starts at the origin, but we're changing it somehow, where is it now located? Can you tell based off of the transformations? If we subtract 2 on the inside and subtract 3 on the outside. Go ahead, Tori. right 2, and down 3. So if it started at the origin, it's now located right 2, down 3. There's our vertex, aka the lowest point in this case. So we're going to connect the open circle to the closed circle, making that vertex the lowest point. Do you see how that first equation only shows up in the section we wanted it to be? Okay, that's why we just use the beginning and ending points as those guides. There's no reason to plug in anything else because those are the ones you start with and end with. Okay? Let's go ahead and try the next one. If you take a look at the domain, we only have to plug in 4 in this case. So if we were to plug in 4, looks like this one's going to be a little tricky because we have a fraction. If we were to plug in 4, we would have 8/3 plus 2. Let's see, adding fractions, we would have to get a common denominator. So 2 is the same as 6/3. 8 plus 6 would be 14/3. How many times does 3 go into 14? 4 times, right? 12. And we have 2 left over. So 14/3, aka 4 and 2/3. So if you plug in 4, you get 4 and 2/3, or 4.66666667. So let's go ahead and plot that point. It's going to be a little rough because it's a decimal, but if we plug in 4, we have 4 and 2/3. Okay, somewhere right there. And notice how it's an open circle because we don't have that bar. All right. What type of equation is this second piece? What type of shape should we be anticipating? Go ahead, Rebecca. It's a linear, it's a line, like mx plus b. Okay, so we only should be drawing a line in this second quadrant here. Okay, how do you typically graph a line? What's the first point you plot, and then what do you do? Yeah.
You should look at the origin and then go up and down.
Sometimes you can start at the origin. You might not always start there, though. The y-intercept. Okay, so notice how the y-intercept is 2. Okay, so I want you to think about it in your heads. If we were to start here and then use our slope, okay, up 2/3, notice how that point is not in the section we want it to be, right? We said the second equation should only show up over here. So I need to go a little bit further with my slope. I'm going to continue to go up 2 and over 3. Is that point now in the section we want? Yeah, so let's go ahead and plot that. If you want to keep going up 2/3, you can. So if we connect the open circle that we know has to be there with the other points we got from the slope, there's the second piece of our piecewise function. Do you notice how that line only shows up within that second region? Okay, so we have nothing over here, like we identified. We only have the parabola in the middle, and we only have the linear on the end. Okay, using those barriers helps me, so I know exactly which one goes where. Okay, let's go ahead and try another one. We'll see how far we get. The bell might ring, but we'll see how far we can get. Let's go ahead and start with our little regions if you want to. All 3 of these domains involve -1, so we really only have one barrier. Notice how the first equation shows up to the left of -1. The middle equation shows up at exactly -1, so I'm going to go ahead and label that exactly on that barrier I drew. And the third equation only shows up to the right, aka greater than -1, so that's the entire right side. Okay, so let's go ahead and start with our first one. We only have to plug in -1 to get kind of a starting point for this first equation. So if we plug in -1 plus 2 would be +1. The absolute value of +1 is still +1 plus another 1 would give us 2. So if we plug in -1, we get out 2. Open or close circle? How can you tell? Good, Rachel? Open, good. There's no bar. Okay, so open circle. Now the rest of this absolute value, what shape of a graph should we be anticipating? Absolute value. Good, Rebecca? A V. Okay, so we should have some type of V-shape graph on this left-hand side. Okay, so this -1 gave us a starting point. Let's maybe go ahead and figure out where the vertex is of that absolute value. Okay, that lowest point or the connection of the two lines in a V. So let's go ahead and use the transformations. Notice how this one moved left 2 and up 1. So we'll move left 2, up 1. It's in the correct region on our graph. So we need a V shape with this being the lowest point connecting that open circle. So we're going to have a little segment to the right and then the other segment of the V to the left. It's almost like a little check mark, but that's your V shape. All right. If we take a look at the next one, if we were to plug in -1 for the x's, okay, in the second equation, what are we going to get out? There's not really an x to plug it into, right? So what's the only number we're going to get out? 3. Tori's saying 3. Exactly. Open or close circle? What do you think, Rebecca? It's not necessarily, okay, so if you were to graph 3, it would be a horizontal line.
It would just be a close circle.
It would just be a closed circle, right? Because notice how this is the only x location of that value 3. You only equal -1. You're only at that point. Okay, so that one's a little different. It's not necessarily a graph, it's just an or a point that you're plotting. Okay, and then the last one, let's go ahead and see if we were to plug in -1. The -1/2 would become a +1, sorry, +1/2, and if we add 5, that would be 5.5. So if we plug in -1, we get out 5.5. There's no bar, so we need another open circle. Okay, about 5.5. This one's going to be another line, right? Mx plus b. Okay, so think about how you would normally plot a line. You would normally go to the y-intercept, right? Which is 5. If I were to put a point there, would I be in the correct region? Yeah, didn't we say 3 was on this entire right side, the third equation? So we can put a point there if you wanted to. If you want more points, you can use the slope. Down 1, right 2, down 1, right 2. And there's your line. So if we check it out, the absolute value only shows up on the left. The number 3 only shows up, okay, on that barrier. And the line only shows up on the right. Okay, it's fitting that piecewise function domain. Okay, we'll go ahead and check out the last two tomorrow. Maybe you can check out some more of the homework problems tonight. Give them a shot.